So here we're going to practice balancing chemical reactions. Now, go ahead, pause the video, and try to balance the reaction that you see right here. Go ahead and pause now. Okay, let's take a look. Now, the way that I like to start these is I like to have a little table here. You know, as chemists, we love our tables. So we have carbon, hydrogen, and oxygen. That's all the atom types on this side and all of the types on that side. Now what I'm going to do is I'm going to get an idea of where I'm at right now. I have 2 carbons. I have 5 plus 1 is 6 for hydrogen, and I've got 1 oxygen plus 2 more, so 3 oxygens on this side. Also, I've spotted this is probably going to be the one that I'm going to balance last when I balance things, because hey, look, it's all oxygens. And as long as I have an even number of oxygens, I'll be able to balance that at the very end. So that'll be a very nice, easy last step for me to do. It's kind of a dead end in the process. Now over here, I'm going to have 1 carbon. I'm going to have 2 plus 1 is 3 oxygens, and I've got 2 hydrogens. Okay, so I've got the right number of oxygens, although that's certainly about to change. That's fine because, like I said, we can do that at the very last piece. Now, I've got an odd number and an even number that's jumping out at me too. What I'm looking at here is how I have to strategize things a little bit. Now, what I want to do is I would typically want to start out with my most complex molecule and try to balance things on it. Since it's got more atoms than anything else, I'm not going to have to balance it right now. I've already got it set up so that I've got one of them for the moment. So I've got 2 carbons. Let's go ahead and balance this one by adding a 2 right there. Now what I'm going to do is I'm going to recount all of the atoms that I have on this side. So I've got 2 carbons. So let's go ahead and get that down. I've got 2 of those. For oxygen, I've now got 2 times 2 is 4, plus 1 is 5. So I'm at 5 oxygens. And for my hydrogens, that remained unchanged on the other one. So I'm at 2. Okay, so that got my carbons balanced. Now let's go ahead and try to balance up my number of hydrogens. Now I've got 2 here, I've got 6 over there, so let's put a 3 in front of this one. So 3 waters. That gets me to have 6 hydrogens. In fact, let me go ahead and erase it all again. I've still got 2 carbons, so I'll have 2. I have 2 times 2 for oxygen, so that's 4. Plus this, so that's 3 more. So 4, 5, 6, 7. So I'm at 7 hydrogens and oxygens. There we are. And then hydrogens, I've got 3 times 2 is 6. Okay, so I don't have an even number of oxygens on each side, and I need to, because when I go to balance this part, I've got to have at least 2 right there. So what I think I'm going to do is I'm going to go ahead and just double everything, just to make things easier for me to work with. Maybe that's overkill, but I can always reduce it down at the very end. So I'm going to do 2, 2, I'm going to do 4, and I'm going to do 6. And let's see what that gets me. So I'm at, let's see, 4 carbons. I'm at 10 hydrogens plus 1. No, sorry. Let's do it this way. 5, 6 times 2, 12. That's better. And now I've got 2 times 1 is 2. 2 times that is 4. There we go. So I've got 4 oxygens. Okay, now I've got all of my atoms accounted for on this side. I come over here. I have 4 carbons. Nowhere else, so that one's set. I've got 4 times 2 for 8, so 8 oxygens, plus 6 more, 8, so that'll be 12 oxygens. Oops. There we are. And then for hydrogen, I've also got 12. That's helped me out quite a bit. So now what I need to do is I need to go ahead and I need to up the ante on this one a little bit. I still need to get 8 more oxygens in there. To make the molecule, that means I'm going to make 4 more molecules. So let's bump this up to a 6. Now, here's how I like to do my check, because notice that step 3 is check. Check to make sure everything's right. I like to kind of have my last step, or what I think will be my last step, be my check, because it's my way of making sure I didn't forget about something or make a mistake when I was adding. That seems silly, but remember, it is easy to make a mistake while you're adding while doing this sort of a process. So for carbon, I currently have 2 inside the molecule, times 2 gives me 4. For hydrogen, I have 6 inside of this molecule, times 2 gives me 12. I have 1 inside the molecule, times 2 gives me 2. I've got 6 times 2 gives me 12, plus those 2 gives me 14 oxygens. All right, so I've got 14 oxygens. Let's make sure I didn't make any mistakes in my balancing by switching to the other side. I've got 4 times 1 for carbon. Now for oxygen, I've got 4 times 2, so that's 8. 6, so 8, that's going to get me to 14 oxygens. And then for hydrogen, no hydrogens here, 2 times 6, that will give me a total of 12. Okay, so this is balanced. Now what I need to do is get to the smallest whole number ratio. I've got my double check, everything's fine, but I've got even, 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 even. That means I do need to reduce everything down. Also notice I didn't change my coefficients there, and that means I did have a mistake in my adding earlier. So it's a good thing I did the double check, right? Not that I would ever do something like that intentionally in a video. So this will be a 1, this one will be a 3, this one will be a 2, and that one will be a 3. That should be my balanced chemical reaction for this equation. If I didn't have my states of matter, I'd go ahead and I'd write them now. Now what we're saying is we have some sort of an alcohol. Now you won't necessarily know that depending on what nomenclature you've had to learn for our covalent molecules. But when it has an OH group on it that looks like this, it'll be an alcohol. There are other kinds of molecules that have OH groups, and you'll get to learn all about them in organic chemistry. For now, I'll just tell you this is an alcohol, so it's going to be a liquid. It's a big enough alcohol that it's staying liquid. This is oxygen, and so we know it's a gas. Carbon dioxide we also know is a gas, unless it's dry ice, at which point it'll be a solid. We don't really work with liquid carbon dioxide. You have to do some funny things to get there, and we'll talk about that when we're talking about ideal gas law a little bit. And water we expect to either be liquid or gas phase under normal conditions. Well, I had a liquid and a gas, and I'm making carbon dioxide and water. That probably means that this is going to be some sort of a flame, because when I spot this, it's a combustion reaction. Remember, combustion reactions don't always mean that there's flame. Flame doesn't always mean it's a combustion reaction. But in this case, that's exactly what would be happening. We're talking about lighting alcohol on fire with oxygen to make carbon dioxide and water. Well, if it's lit on fire, I expect that the state of matter for that water is going to be the gas phase. It's going to be coming off as steam. And yes, it'll condense later on. So you could probably still get away with writing liquid if you're talking about a longer term product. But that's going to have some important implications when we're talking about energies and reactions in the thermochemistry chapter. So we want to make sure that we're trying to go for the most immediate change. And the most immediate change would be into gas rather than liquid. So that would be our balanced reaction for this problem.